Hello, and welcome to any edition of H.E.L Explains with your host, Dr. Mario Torres Rodrigo. And today we're going to see how adiabatic calorimetry can help us make our battery system safer. The world is shifting away from fossil fuels, and batteries are powering this transition. But with higher densities also comes increased risks. Reports of battery fires and explosions are becoming more and more common in the media, and this is oftentimes linked to processes known as thermal runaways. A lithium-ion battery, the more common ones that we have nowadays, are normally composed of three different components. We have an anode, we have a cathode, and in the middle, connecting both of them, we have an electrolyte. All of these parts can become unstable under certain stress conditions. And when they are under stress, they can undergo decomposition reactions in which the components of these parts of the battery can cleave and become smaller molecules. And in this process, sometimes energy can be released, further increasing thermal stress within the battery. These reactions, in most of the cases, are exothermic. They release energy, and sometimes one of the products of this decomposition are gases. If not controlled, this leads to dangerous escalations, what we have called before thermal runaways. Adiabatic calorimetry offers us insights into the process of a thermal runaway, so it allows us to get to know what the worst case scenario would be. Unlike other methods that rely on external heating, adiabatic calorimetry tracks the battery's own heat generation without letting that heat escape to the environment. Using adiabatic calorimetry, we can characterize some of the critical parameters on this thermal runaway process. For example, the onset temperature, the temperature at which the reactions inside of the battery are accelerating, getting into this thermal runaway. The self-heating rate, how fast the battery is becoming hotter and hotter. And finally, the pressure evolution, how much gas is being generated from the battery and it accumulates within the structure. These insights help engineers and scientists design safer batteries and understand how fast, and why thermal runaways occur. Adiabatic calorimetry is not only about confirming whether the battery is safe or not, but also how we can develop systems that are going to keep the battery safer. This includes fine-tune of the battery management systems, cut-off thresholds, selecting safer materials, design venting and extinguishing systems, and optimizing for the different states of charge. It's not about reacting to the danger, it's about being proactive and how to design the danger out of the battery. In certain places, like in China, adiabatic battery testing has become enforced by national standards, and in other places like the US and elsewhere, it's rapidly being recommended as a testing and integrated into compliance frameworks. Access to global markets depends on the level of rigorous safety data that we can provide about our batteries. As batteries become more and more the core of what powers our world, from cars to homes to entire grid, safety testing must evolve in parallel. Adiabatic calorimetry gives us answers that are not only theoretical, but also they are rooted in real measurable danger. So, as we can see, adiabatic calorimetry provides insight into some critical questions like, what reactions drive batteries failure? How fast do these reactions escalate? And how can we intervene in time? With adiabatic calorimetry, the question isn't whether we should use it, it's when we are going to start using it. My name is Dr. Mario Torres Rodrigo, and I'm the applications leader here at H.E.L. If you have any questions, if you have any comments, please come and speak to us. Thank you very much.